everyone. So, real champions are here today after the conference dinner. On the other hand, there are classical potentials. As a computational physicist, I have a dream to do computational experiments. Hello, everyone. I'm Rina Ibragimova. I'm a postdoc at Aalto University in Finland, and I'm a computational physicist. And I do theoretical modeling of different materials, in fact, using machine learning approaches. So in our group, we developed the machine learning interatomic potentials, which help us to achieve very high accuracy in our computations and at a very low cost. So that means that we can do much bigger systems, compare, let's say, to the conventional methods of DFT, and much longer dynamics, and do almost DFT accuracy of our simulations. So we have different interatomic potentials which are fitted based on a large amount of data, and those potentials are for amorphous carbon, for carbon and hydrogen based systems, and for oxygenated amorphous carbon systems. My domain is in developing the general purpose carbon and hydrogen interatomic potential. And this is quite challenging task because we want to unify under same methodology, under same potential description of hydrocarbons, different molecules, and solid or amorphous materials. We want to be able to describe those materials at very wide range of conditions, as low temperatures, low pressures, and higher temperatures and really high pressures. We want to describe them very accurately, so we add the van der Waals interaction to that, and some level of reactivity. And this potential we developed, we did a lot of different validation and different tests, but one of the results I showed today at my talk were about generative melt quench simulations, where we simply vary the concentration of carbon and hydrogen in simulation cell, and we perform a calculation at different temperatures. At 3000 Kelvin, at 2500 Kelvin, and then we quench those structures to the room temperature. And depending on the concentration of carbon and hydrogen in simulation cell and different temperatures and different quenching rates, we can obtain enormous amount of different structures, starting from some molecules like simple alkanes, more complex alkanes, increasing the concentration of carbon in a cell that we can get aromatics, and at much higher concentrations of carbon we can get even hydrogenated amorphous carbon in our cell. So this shows the power of machine learning interatomic potentials, that basically we can reproduce very well-known structures without providing this structure implicitly, but providing just those parameters as temperature and cooling rates. Yeah, so I think that's it in a nutshell. I think it's a great tool to study the systems such as amorphous carbon, hydrogenated amorphous carbon, which are difficult to study with conventional quantum mechanical methods due to the really big size, and this is a great tool to do molecular dynamics calculations for results. And my supervisor Miguel Caro, and I thank you for your attention and welcoming your question.
Thank you very much.